Yes, so we are on. We are recording now, so people can watch this on YouTube. Finger crossed, nothing goes wrong. Okay, so welcome to session 19 of 20. So we are really nearing the end, the end of this very long crash course. I don't even remember when we started. Was it in spring or something? It's a bit unusual to. It went on forever. Like I know some people are having like a fatigue, so don't worry. There's a the last session will come in soon, and you will have a break, and maybe you can focus on other stuff like the measure theory stuff. Yeah, George, you want to say something?
I would just say I think 20 lectures is a semester's worth in traditional terms.
Yeah, it's 20 sessions. Yeah, obviously we could have closed this earlier if we didn't go through all this starting from like all these semi groups and all this stuff. Yeah, and also because we are doing bi-weekly, that also added the stuff with some interruptions because of bank holidays and other stuff, and also my availability. So we are here. So in the last session we covered the orthogonal group and the special orthogonal group. Today we'll focus on these other guys, the unitary group and the special unitary group. It's mostly just to introduce you. Most of you already know about these, but it's just for those who are not aware of them, it's just to see. And I will be giving some hints about their Lie group properties. Obviously we won't discuss that because we don't. You need more. We don't have the tool set or the language for us to be able to discuss them in the context of Lie groups. But I will be giving hints, about their dimensions, for example, because they are manifolds, their compactness, connectivity, and this connectedness, not connectivity, and so on. Yeah, so you will see some very interesting stuff in here. At least have a hint. This also hopefully will motivate you to take the Lie group course, which is what will come after this. The start date is actually something that we need to decide. I guess at this point, maybe you might as well have it in early next year, no? Instead of jumping straight, so you can have some break to review a bit of topology. We will do that. I saw in the chat before people asking about fundamental group and these things. Before in the early parts of the Lie group course, we'll do some review of topology and differential geometry. And cover some other stuff that we didn't cover in the differential geometry and topology crash course. So we will do the review. But I still encourage you to go and still take the first 5 or 6 sessions of the topology and differential geometry crash course, because if you are seeing this for the first time in the next crash course, it might be you probably not going to feel that comfortable. So it's worth taking it and then taking it again in the review, so you will feel far more comfortable. So I really recommend you to still, even though we will do a review in the start of the course, Lie group course, still I recommend you to take the other crash course, so that way you feel more comfortable. Because things will start soon going. Yeah, go ahead.
Take another nibble on the abstraction pill.
Yeah. Because if you wait for the review in that we will do in the Lie group course, it will be really very very narrow, like very how do you say, compressed review. So you will struggle if it's the first time you never heard of manifold, you never heard of a topological space and these things. So you better take the other crash course, and then you will feel more comfortable. Okay, so just to crack on, I hope I didn't make any typos, because this is the danger of copy and paste, because I was copying LaTeX. It's just to change R with C, so some places I will probably have typos, but that's a good thing for the eagle eyes to correct. Yeah, so again, this is such a convention, really. So we will write this to denote the set of all n by n matrices over, you see, there's a typo here, over the complex numbers, so it's not over the reals. There you go. So yeah, over the complex numbers. There you go, the first typo. Okay, so yeah,
Yes, and that's throughout. You need to replace real by complex throughout.
Complex, yeah. So that's the thing, because obviously I copied this from the previous thing. This is the danger of doing that copy and paste. Sometimes you forget to correct. So this is over the complex numbers. Obviously, I think it's implicit here. I will correct this slide, obviously. Yeah. So yeah. So again, just like we did with the real case in the last session, we've seen that this forms an abelian group under addition, but it does not form a non-abelian group under multiplication, because obviously this is set as it says here. This is the set of all matrices, of all n by n matrices. So therefore, it includes like the zero matrix, for instance. I guess this trivially tells you that this cannot be a group, because that's not invertible, and not even talk about the other ones that are not invertible as well. So there are n by n matrices that are not invertible. Yeah, so it cannot be group, because there are elements in this that don't have inverses. Okay. Another thing is just like in the real case, when you have n by n complex matrix, this induces a linear map from the space Cn to Cn, right? Equipped with the vector space structure, the complex vector space structure, right? And likewise, similar to the case of with the real case example, any linear map from Cn to Cn also induces a matrix, an n by n complex matrix. So this means linear maps on Cn are the same thing as n by n matrices over Cn. So linear maps are the same thing as n by n complex matrices. Okay, when we are talking about Cn. George, did you see any typo there?
No, aside from anything about real and complex and R and C.
Okay.
I think all of the C's look good.
Yeah, okay. Okay, so now similar to the definition, and another thing, you just pay attention on the numbering of the definitions. I might have gotten them the thing wrong. Let's see. So I think this meant to be okay. Yeah, this one is definition 1.0. Yeah. Okay, so far so good. Okay, so just similar to the last session with the real case, we say a subset of n by n complex matrices is this slide is going. A subset of the n by n complex matrices is a complex matrix group if it's a group under the ordinary matrix multiplication. Obviously, that also implies this thing. Okay, so it's a matrix group if it is a group. Okay, so it has to follow the thing. It has to follow the group axioms, right? So you need to check. So this is what we call a complex matrix group. Okay, a subset of n by n matrices. That's a group. Okay, so just like in the last case, we can also ask anything. If it's a group, then we can ask everything that we can ask about groups. About actions, cosets, orbits, and so on. Okay.
I guess it's clear that G actions are actions on the vector space Cn.
Not necessarily. It can be action, an abstract group action, right? That's natural. That's a natural action. Obviously, that's what's mostly used. But the group itself can act. It can act abstractly on any set.
Okay, thank you.
In fact, in the next session, I think in the representation thing, we will see the action of some of these groups on finite groups, on finite sets, for instance. Okay, the general linear group, just like in the case, I hope I didn't make mistake. Again, this is typo, copy and paste. I just replace R with C from the previous session. So eagle eyes, please. So the general, so this is a proposition again. The same procedure you did to prove the other one in the real case is the same here. So the general linear group over C is the set of all invertible n by n complex matrices. Okay, so this is a group under ordinary matrix multiplication, and you have the same hint as last time. So now comes the hint I was telling you about, the motivation. So subtle hints, because both of them, so the complex general linear group and the real general linear groups are all Lie groups. But look at the thing. Let's see some subtle facts about them. So the complex one is non-compact connected Lie group. So it's non-compact, but it's connected. Whereas the real case is non-compact but disconnected. So you see the subtle differences here. Okay, and I'm using here, actually notice this thing. You won't see this, you won't understand what I mean here. I'm saying real dimension. Okay, it has complex dimension and real dimension. Okay. So this to do with obviously you can view you can view it as a complex. You can also view it as any complex matrix. You can view it also as a real matrix. It's actually, that's isomorphic to GL of to a subgroup of GL 2n of R. So this this is something you will understand in the Lie groups. Yeah, go ahead.
On the real dimension, is that 2n squared, or should there be parentheses 2n, n parentheses squared? Might be my misunderstanding.
I'm pretty sure. Is this? I don't think it's a typo. I think it's right. Yeah, okay. 2n squared. Yeah.
Okay, that's my misunderstanding then. Okay.
Yeah. So this is actually one of the things that you will see on the thing on the Lie group section, the thing of complex manifold versus real manifold stuff. Sometimes the subtlety, there are certain properties there that are very interesting to observe in terms of behavior. You will see there will be another surprise actually. Yeah.
Okay, so, I think I got it. The n squared is actually direct sum, not tensor product. Okay, sorry about that.
Okay, no problem. I see my screen, so I freeze a bit. Let's see on the chat. Is there anything here?
Nothing new.
Okay, so nothing new exactly, because this is more or less, apart from this subtlety here, obviously you don't know what, this is where actually, in the Lie group section, you will learn why this is a manifold, Yeah, because, this crash course is algebraic, so it's not topological. So, yeah, but you will learn about this in the Lie group section, why it's a manifold, and obviously being a manifold, topological space, and it's you can talk about connectivity, you can talk about compactness and so on.
You might be able to talk about compactness just in the real sense, using the real norm, and closed and bounded rather than the abstract topological definition.
Yeah, it is much more easier to grasp, if you will, from that angle. Yeah. So here's another thing. So I'm using proposition instead of saying like a definition, because I encourage you to try to actually prove this as opposed to defining, so you can prove. So the other one is the other group, matrix groups, that we need to worry. Interesting is the complex special linear group. There is the analog in the real case. We saw that before. So this is similarly the set of all invertible complex matrices with determinant 1. Okay, so this is a subgroup also of GL of NC. So it means that it's a matrix group, a complex matrix group, right? Yeah. And now, because in the last session we covered its real cousin, let's look at the difference here. So the complex one is non-compact connected Lie group of complex dimension, which is this, and real dimension, which is this. Yeah, you can do the distribution using the distribution law to calculate the actual the final the thing the number. Yeah.
Okay.
So,
yes.
Yeah. Yeah. So far, so good between them. There's no disparity here, unless I made any typo. So this is compact connected, and this is, sorry, this is non-compact connected. This is also non-compact connected. That's the claim. And now let's move on. So let's see another example of a, so we have seen these. So these are matrix groups. Let's, actually, I forgot to challenge you with this. So given the multiplicative group of non-zero complex numbers, obviously the determinant function, is that takes a non-invertible, an invertible matrix to its determinant is a group homomorphism. Okay, and the claim is that the kernel of this is actually this guy. And now we have seen the general two examples of complex matrix groups, right? So we have seen the general linear group, and we have seen this. So now let's see whether we can get other examples. Let's see this example here. This example. For that, I'll give you, let's go back to, this will be embarrassing if I got this wrong. The kindergarten stuff we learn in high school or something, or, or school, complex numbers. Okay, there's someone on the chat. Is that, can we go back for a minute, compare the definitions of linear versus special linear group? Yeah. Have I made any typo? Okay, so the linear group, the general linear group is the group of matrices of non-zero determinants. So this means the group of invertible matrices, complex matrices, right? Have I made any typo? Obviously, if the determinant is zero, then the determinant can be anything. It can be like any non-zero number, right, including 1. So now the special linear group is that we are narrowing the type of elements of the invertible matrices. In this case, we are only focusing on the ones with the determinant equals 1. Yeah. Okay. Yeah, no problem. Okay, so let's see now complex numbers, kindergarten stuff. So if you have a complex number, right, in this form, let's say a equals x plus I y, where I forgot to add, this is the imaginary part, right? You all know this. I don't want to insult you. Yeah. So the conjugate written, a bar is written like this, is actually x minus, iy. Okay. Now, this is the thing. It's very, very important to note in some textbooks, especially the ones written by physicists, they don't use the a bar to denote the conjugate of this. They use the a star. Mathematicians don't do this. So when you pick a linear algebra book or other books in these topics that we are going through, make sure you know whether it's a mathematician or a physicist who wrote it, because otherwise the notation might be very confusing and you might confuse yourself. Okay. So in here we'll use, yeah.
Small typo, unless my eyes are off. It looks like warming instead of warning, but that might be my eyes.
Where is it? Okay, yeah, there is a typo here. Yeah, so it meant to be warning, not warming. Yeah, this is that's right. Yeah. Sorry for that. I knew. This is again copy paste. Yeah. So this means there is more typos to come because I think I used this somewhere. Yeah. So it's warning, not warming. So I will correct the slide. Okay. Yeah. Sorry for that. Now that we have this kindergarten refresh of about complex numbers, let's build this set, right? Made of these 2x2 matrices, right? With these properties, you know, where alpha, beta are complex numbers with these properties. So the claim is that this is a subgroup of the, you know, the general linear group of 2x2 matrices, complex matrices. Okay. So the claim is this is a group. Okay. So this is actually a very interesting group. I don't know if some of you can anyone see which group is this? This is why I brought, it will become obvious later, but this is actually an interesting group. And in fact, you will see in the Lie group section, this group is actually as smooth manifold is diffeomorphic to the 3 sphere. Okay, so there is a diffeomorphism between them. Okay.
Yeah, it seems clear that the norm of alpha and beta is 1.
Yeah. Okay, so which group is this? It's a very famous group in these guys. Can anyone give a hint? Okay, Amir is saying Hermitian unitary. Okay, Dimitri saying Mobius transformation. Okay, there are all sorts of clues there. Let's see. Okay, maybe we'll this is one of the reasons, because the other group we define it in terms of determinants and these things, not in this Yeah. Remember these guys, the betas are complex numbers, right? So
yeah, so that you actually need to show that it's Hermitian. I think the other hint you gave about it being a 3 sphere is a big hint geometrically.
Okay.
Whether
there you go.
the norm being 1.
So Berend is saying U of bracket. Okay. Quantum computing, guys. Or physics, guys. Is it obvious? Can you see which group is this actually? You will see this defined in a different way. This is just obviously with this in the case of n equals 2, we can define it this way, but there's another way of defining it. Maybe then you will see which group is this. Okay, it's actually interesting that that's why I put it matrix group in disguise. I hope, is that how you write disguise? I know I use S.
Yeah.
Is it disguise with S or Z?
It's an S, yes.
Yeah. Even in America, you don't use Z?
No, yeah, it's because it's followed by a G that it sounds like a Z rather than an S.
Okay.
Part of the English pronunciation that's common between England and America.
Okay. You see, in this quantum formalism, you get languages as well. You don't just get,
But yeah,
Okay.
Amir confirms correct spelling.
Okay, thank you. Okay, there you go.
Dimitri's.
Yeah, Dimitri found it. Yeah, so it's actually SU2. This is SU2 in disguise. Yeah. So yeah, it will become obvious later that this is equivalent to the other definition. Yeah. So this is indeed SU2 in disguise, this group. Okay, but we don't know what SU2 is yet. So let's, for those of you who don't know that, now the next couple slides will be to take you to that direction. So the first thing, I hope I didn't make a mistake here, because obviously there's so many entries there. So given a square matrix, right? We define like a square matrix, complex matrix A. We define its conjugate as this. So this is basically essentially, you have the original matrix to its conjugate. You just take the conjugate of the entry, the complex conjugate of the entries. This is what I'm saying here. I hope it's not confusing.
So it's just entry-wise conjugates.
Yeah, entry-wise. Yeah. Okay. Now, this is another warning that if you pick a book written by a physicist, they won't write this A bar for the matrix. They will write A star. Mathematicians actually reserve this for something else. There's something called involution and these things. When you study C star algebras, you'll learn this. So again, it's very important when you pick a book, make sure you know whether it's a physicist or a mathematician who picked it.
A good book will have one little page at the beginning of the notation they're using throughout.
And the convention, yeah. Okay. So this is what what's called, the conjugate. So the conjugate of this matrix is essentially just take the conjugates of the individual entries, right? As of this definition here. Okay. Now, the conjugate transpose, or there's a name for it, Hermitian conjugate, I believe it's called, is defined like this. Okay, so when you have the matrix A, it doesn't matter how you do it, it's defined as A star. So you see, this is the mathematician's notation. Huh? So in the previous, the physicists would use the star for something else. You see, this is where you have to be very, very careful. I'm using the mathematician notation, but soon I'll satisfy the physicists in a minute, because we'll use the physicist notation for the dagger, using the dagger thing. Yeah. So the conjugate transpose is essentially this. You take A star, you take the conjugate as of this thing here, and then you transpose it. Okay, it doesn't matter how you do it. You could also transpose it and then take the conjugate. It means the same thing. You yield the same. The final matrix will be the same. Okay. Now, physicists don't use A star for this. They use A dagger. So we will use this. We'll use A dagger because it's a little bit fancier notation.
I like it because, at least in math, star is very overloaded.
Yeah. So this is something that I guess physicists, the influence on physicists, one of those good influences that physicists have in mathematical notation. Yeah. Okay. So A dagger. Yeah. So this is what's called conjugate transpose, or Hermitian conjugate. I believe that's another name for it. And now you have these very beautiful properties. I hope I didn't make any typos, but I challenge you to try to prove this, even just for n 2 by 2 matrices. Okay, it's very, very nice properties. The first one, obviously, is that if you take the dagger of the dagger, will take you back to the same to the original matrix, right? And then you have this nice properties here, and so on. Okay, and also if A is invertible, then its dagger is also invertible. This is very nice.
It's a little subtle that scalar multiplication isn't directly linear. I guess you could call it conjugate linear.
Yeah. So I try to for you to try to prove this. Even with if you can just take some examples, even work out, see some example, even if you cannot provide a general proof, just play around with this to see. Yeah. So you will be asking, why do we need this? Well, we need this in order to get to unitary groups. I could have actually gone directly, but I decided to, refresh you on this. And now the unitary group. So I'll put this also as a proposition. So this set, the set of all invertible complex n by n matrices that satisfies this is a subgroup of the general linear group over C. Okay. So this is called the unitary group. Okay. So notice this. This means that this. This means that the A dagger is equals to the thing, obviously to the inverse of A. Have I made any typo there in the definition?
Looks good.
Let's see, George.
I'm just squinting at the screen. It looks good.
Okay. Anyone else? Have I made any typo there? Do you agree that's the definition of the unitary group? Okay. So another thing is that the unitary group are indeed the linear isometries, of Cn, of as an inner product space, right? As a normed space, so it preserves it, so it doesn't change. It doesn't change the length of the vectors and so on. And obviously, the unitary is very important group with so many applications in physics and also quantum computation, right? The quantum gates they belong to this group. Okay, so let's go back again to the facts. So this is let's say this is UN is the complex version, let's say, of the tamed real orthogonal real case, essentially. But let's see some subtle differences between them. Now look at this. UN is compact and connected Lie group of dimension n square. I hope I got this right. You will be able to see this actually because I have some table thanks to the interesting conversations you guys were having earlier. So I put some table. So you will be able to confirm whether this is true. Yeah. And ON, you will actually, one thing on Lie groups, there is a way of calculating this this dimension stuff. It is something that you will learn how to do. Anything in why this is the case. Where is this dimension stuff is coming from? Okay. So UN, the unitary group, is compact and connected with real dimension. Notice this. I'm only saying with real dimension. If I'm not using complex dimension here, there's something very interesting happening here. Even though the unitary group has made the entries are complex, it happens to be a real Lie group. Yeah, this is something that you will understand later on the thing on the course. So the orthogonal group, real, this is real, obviously, is compact but disconnected. I hope I also got this right. Okay, the dimension, definitely, this is the dimension of it. So look at this is just hint because you will not understand why this is the case until we go to the the Lie group course. But this is just to show you how interesting how this thing of when you add the topological lenses to it, to this, algebraically, this is all like you might look, okay, yeah, these things are more or less the same thing, algebraically not much difference, but as soon as you start to add the topology, your topology lenses, you start to see some very interesting stuff. And this is just scratch of the surface that what you will see in anything when you take the Lie group course. Okay, very interesting. George, I see you. It's like you have you noticed something? I think you are muted.
No, it looks good. I'm just thinking about the geometry of it, but it looks good.
Yeah. Okay. Okay, so now let's go to the special unitary group. Okay, so the special unitary group is a set of all unitary matrices with determinant 1. Okay, so the claim is obviously this is a subgroup of UN. Okay, so let's say this is, again, I'm being a bit thing like it's a complex version of this guy. Okay, and also is it clear that the special unitary group is an intersection between the unitary group and the special linear group? Is it clear there? Right? Because it says here, it's all the elements of the determinant 1, right? It has to be unitary and it has to have determinant 1. And the matrices in a thing, invertible matrices with determinant 1 are also, they are the ones who live in the special linear group, right? Let me go back so you can see this. Now this, yeah, so here's the definition of the special linear group, right? Is the set of all invertible matrices, complex n by n matrices with the determinant 1, okay? Let's go back here. And here we are saying the set of all unitary matrices with the determinant 1. So clearly, the elements of this have to live in both, in their intersection, right? Are we on the same page? Correct? George, you agree? I think you are muted, George. How's the chat? I stopped seeing any updates. Are we all on the same page?
Yes, the chat is quiet. And when I nod, it means agreement. Sorry if that's confusing.
Anyone else on the audience is confused about this? Are we all on the same page? Yeah? Okay, yeah, good. And there you go. So this is exactly, so the other group, you can verify actually the determinant of this is 1. Okay, so therefore this SU, this is SU2. This group, this thing we were calling a group in disguise, it is. Yeah. Yeah, I'm just using, I could have said this is like, obviously it is a subgroup. This is to, a subgroup is a group, right? This is another way of saying that it's a group, right? In this case, this is, I'm doing this just to hint the connection that it's actually, it's a group embedded in this one, in this larger one, right? Because it's coming from there. But it is a group on its own right. So when you do other stuff, you can just pick it itself as a thing. It's restrict. It's a special type of group within the unitary group itself, right? It has a very interesting properties. So you can do stuff on its own. In fact, I forgot to add this in physics, for example. SU, yeah, what is it? So Amir is saying, let's try to help Amir to see. So Amir, are you saying that this? Are you saying this is a subgroup of?
I think he means that it might be a subgroup of a subgroup as well. And he's asking, is it normal to use the most restricted group as parent if you have nested subgroups?
Yeah, I'm just as I said, I'm just using this here because the construction is done on the thing on using the UN, right? You know, so we are restricting the special. So we need, first of all, we are constructing. It's clear that we need what we want. One thing that we want from SUN is that it has to be unitary. Okay, so that's the first thing. Okay, so it needs to be a unitary, an element of the unitary. But then we went further to say, like, you know, we need it also to have determinant 1.
Yes, I think maybe to help Amir out, we're referring to immediate parents. That helps. But it's an interesting question what the relationships are between the various subgroups, whether they're subgroups of each other and so forth.
And there are other groups that we haven't actually covered in these things that you will come across later, actually, in the Lie group stuff. Yeah, very, very interesting groups. In the real case, for instance, like, you know, the symplectic, for example, the Poincaré group, all this stuff. Yeah, so you are actually just scrapping. Yeah.
But right now, all we are doing is specializing step by step.
Yeah.
We're specializing to invertible matrices, then specializing to unitary matrices, and then within that specializing to determinant 1.
Yeah. Any other comment, Amir? You can come on the stage.
Yeah, I think it's what he meant in his last comment is that you don't lose it being a subgroup of SL then. Yeah.
Okay, so another thing, as a side note, as a Lie group, so this is compact and connected with, again, remember with the unitary group, we only talk about real dimensions. So this is also in the case we are talking about. Okay, yeah, no worries, yeah. Yeah, no worries, Amir. Yeah.
Thank you, Amir. It helps to
interesting.
pause
Yeah,
and think. Taxonomy is kind of what we are doing.
Yeah. So SUN, let's see how it compares to SON. Okay, so SUN is compact and connected Lie group with real dimension n square minus 1. Okay, so I haven't mentioned complex dimension. You remember with the special linear group, there is a complex dimension, I believe. Let's go back to it. So this is another one that we are only talking about real dimension. Where is it?
On the bullet point 1.
Yeah, so its complex dimension is this, and its real dimension is this. Okay, you will understand what all this, the difference between complex and real dimension in the next course. Okay, I'm just hinting at the thing, you know, at the surface, you know, algebraically, you know, they are very boring. They might look like they have more or less, you know, same thing, you know, but once you start to add topological, you know, lenses into these things, you know, they start to become very, very interesting and very tricky, very subtle. That's the reason. Oops. Yeah. So SON happens to be compact and also a connected Lie group. So there's no thing. Obviously, the dimensions. This one has real dimension. This one has a real dimension. This question is, you can do the thing. Are these dimensions the same? If you do the calculation here, you can verify. Okay. So this is it. So you know now the complex matrix groups that we are interested in, the most interesting ones. In the final session, we will introduction to representation theory, and we will focus on the representation theory of these groups that we went through today. Like the unitary group, the special unitary group. These are the type of representations that have applications in physics, in quantum computations, and so on. Okay. So in the next session, we will focus on representation of groups. We'll start abstract, and then we will specialize on the representation of the unitary and the special unitary groups. You'll see some examples and some challenges. Now, someone was talking about I think it was Emilio. What was it about? The fundamental group and all these things. This is something that you will do. In fact, before that, I have a challenge. This is like maybe a trivial challenge. I call it SUN challenge. Is given this this determinant, what is the kernel of it? And also, is it true that SUN is a normal subgroup of UN? Yeah, Baran says like mathematician taxonomy. Yeah. So yeah. So this is like a I wake up, type of thing. I hope I didn't make any typos. If I do, it's a good thing because you will be able to correct me. And now here's a table. It's a bit messy. I took this because I didn't have time to do it myself. So I remember this guy had this thing. There's an old textbook I had. I remember it had this table. So I will try to clean this table and make it more thing. But for those of you who are interested in things like fundamental groups, here you can see the individual groups and then see their fundamental group. Okay, like So this is something that you will, for those of you who haven't taken this is like what is this? All this the little g, there is a Lie algebra and so on. This is something that you will learn. Believe me, you will understand this once you take the Lie group course and these things. You will understand this. Yeah.
Well,
I haven't even checked whether there are any typos in here. I just took some just for you to. Yeah, go ahead, George.
Now this makes it clear to me what was meant by fundamental group of a group. It's fundamental group of the space.
Yeah.
Okay, thank you.
Remember these groups, Lie groups are topological spaces, right? So you can talk about these topological notions. Okay. Okay, people are fine. Yeah. So this is something that you will learn on the thing on the Lie group section. The pi. This is what denotes these. So this pi 1 of G. This is the fundamental group of each of the groups. So the fundamental group of it's just saying this is Z2 for n equals 10. So you have the groups here, and then on the thing you have their fundamental groups here. Yeah, the other one is the covering stuff. To understand this, we have to. This is in the differential and topology course. We didn't go through this, through the fundamental group. Yeah. So this is just for those who are curious, the ones commenting on the thing like Emilio to look at this. You will understand this table once we go through, what all these things mean. Okay.
Okay, a couple more messages.
Yeah.
Oh, Amir is asking what pi stands for. Pi stands for either the fundamental group pi sub 0 or the next one up, pi sub 1.
Yeah.
But that's the same question from Bob.
Bob, yeah. You will learn all this in the thing. Yeah, go ahead.
Pi is just the standard note. Well, pi 0 is the standard notation for the fundamental group. Pi sub 1 is a related group.
you will get all this in the review of. I didn't want to add this. In fact, I will check this to clean it up, the table a little bit to organize it. But this is, we will go through the review of this, on topology for you how to calculate, how to compute this. Obviously this is a bit of algebraic topology here. Okay, so this thing, okay, I'm going this way. This thing will be available again on the recording. And yeah, I look forward for the next session where we'll do a bit of representation theory and then focus in the context of these, the complex matrix groups that, we cover today, the unitary, the special unitary in particular. I think I can stop recording for the YouTube audience. The next session is scheduled for in 2 weeks' time, right? On the 9th of December. So that's the last session.
Okay, so if it's in 2 weeks, and if everybody's agreed on that, I'm again willing to have a last study session next week.
Next week, yeah.
And I hope I'm better prepared in reviewing